the chemistry of airbags. Airbag technology must know the difference between a minor and a major crash. This is crucial to knowing when the car needs to destroy itself completely in order to protect the passenger, or if it's just a minor thing. It is also worthy of noting that 72.8% of cars have airbags. This means that many people rely on this technology. Also, 699,000 vehicles crash every year only in Mexico. This means that a lot of people crash and there is a lot of use for airbags. Also, it is worthy of noting that airbags must deploy in less than 40 milliseconds in order to be completely effective and safe. The chemical reactions in the airbags start with sodium nitride. This separates into a sodium atom and nitrogen gas. The sodium atom is very unstable and therefore it must react with potassium nitrate in order to produce potassium oxide, sodium oxide, and nitrogen gas. Finally, the potassium oxide combines with the sodium oxide and silicon oxide is also added to the mix in order to produce alkaline silicate, which is the final product and that expands into the airbag, also known as glass. In the ideal gas law, we can see that the pressure is 1 atmosphere, the R is a constant, and the temperature is the average room temperature, which is 25 Celsius or 298 Kelvin. We can then substitute this to know how many moles are needed in order to complete the airbag, which needs 67 liters of volume. This equation shows that we need 2.74 moles in order to complete the 67 liters of the airbag.
So as my buddy said, there are 3 chemical reactions going on here. In the first one, we have sodium azide. This is a highly reactive crystalline ionic solid which reacts with heat, and this creates the nitrogen and the sodium different and separately. Since sodium is highly reactive to anything, including water, it must be synthesized. Therefore, it reacts with potassium nitrate to create what is called the sodium oxide and also more nitrogen gas. But this is also somewhat toxic and it's another crystalline solid. Then silicon oxide is added to the reaction. This is the third reaction, which silicon oxide is another crystalline ionic solid, and this creates alkaline silicate glass. This is an amorphous solid which is non-toxic, and since it's amorphous, it has a non-three-dimensional shape in its atomic structure, and it's completely harmless to humans. Therefore, that means that when the car crashes, the airbag can be disposed of without any proper restrictions or safety measures. It can be just recycled or thrown away in a trash can, in a city trash can.
According to our research, the enthalpy of the first 2 reactions that take place when the airbag deploys have a negative enthalpy. This means that both of these reactions are exothermic, while the third reaction has a positive enthalpy. This means that it is an endothermic reaction.
Meanwhile, the entropy in the first reaction is positive, meaning that the reaction tends to order it, while the second and third reaction have a negative entropy sign, which means that the reaction tends to be a little bit disordered than the first one. While in the Gibbs free energy, we have a negative sign in the first reaction, which means that it is a spontaneous reaction, and in the second also, which means that it favors the formation of products under normal circumstances. And in the third reaction, we have a positive sign of Gibbs free energy, which means that it is a non-spontaneous reaction.
To conclude, we can see that airbags can save lives by reducing the pressure exerted by maximizing the area.
Sodium in the first reaction must be reacted with potassium nitrate because it is toxic and must be eliminated.
And it is important that we properly handle the chemicals released during the chemical reactions to avoid harming any human passengers in the vehicle.
Thank you very much.